A stone house built centuries ago with no boiler, no radiator, no central heating of any kind uses 38% less heating energy than the modern home right beside it. Thick walls, compact layouts, precise solar orientation, these were strategies that made mechanical heating unnecessary. They worked, and then we stopped building them, not because they failed, but for reasons most people have never been told. A home that stays warm without a furnace relies on more than just thick walls. It's the result of several strategies working together, each with a clear purpose. Start with the walls themselves. Built from stone, brick, or earth, their thickness isn't just for strength, it gives the building what scientists call thermal mass. This means the walls act like a giant heat battery. During the day, they absorb warmth from the sun or even from a small fire. When temperatures drop at night, that stored heat slowly seeps back out, keeping rooms comfortable long after the fire has died down. The shape of the house matters, too. Compact floor plans, think square or rectangular layouts with rooms clustered close together reduce the amount of outside wall exposed to the cold. The less surface area there is, the less heat can escape. In these homes, every square meter of wall does double duty. It holds up the roof and helps manage the indoor climate. Windows are small and placed with care. Large panes lose heat quickly, so older homes keep them modest, often set deep into the walls. Builders position windows to catch the low winter sun, especially on the south side in colder regions. This lets sunlight pour in when it is needed most, boosting the heat stored in the walls and floors. Orientation is another quiet tool. Traditional builders paid close attention to where the sun rises and sets, turning the longest side of the house toward the winter sun. Roof overhangs are sized to block harsh summer rays while letting in the gentle warmth of winter light. The result is a building that works with nature, not against it. These elements, thick walls, high thermal mass, compact shapes, careful window placement, and solar orientation combine to create a home that holds onto heat naturally. In the next moments, these ideas will come alive in real-world examples, showing how centuries-old design can outperform many modern systems. Ancient Rome's baths of Caracalla rose from the city like a monument to comfort. Their concrete vaults, some nearly 4 meters thick, trapped heat from the hypocaust below. Even after the fires died, the walls radiated warmth for hours, letting families and bathers linger in steady comfort long after sunset. Here, stone itself became a quiet source of heat, proof that design could outlast the flames. In Persia's deserts, the Yakchal stood as a silent answer to the relentless sun. Built partly underground and crowned with thick brick, it kept its interior up to 15 degrees cooler than the air outside. The secret lay in the Earth's insulation and the dome's mass. By day, the structure absorbed heat. By night, it released coolness, preserving ice for months without a single machine. High in the Austrian Alps, chalets with stone walls nearly a meter thick sheltered families from the cold. When winter dropped temperatures far below freezing, the inside stayed between 12 and 15 degrees Celsius. A single hearth, used sparingly, was enough. Once warmed, the walls let their warmth drift through the night, making thick socks and blankets the only extra insulation needed. In New Mexico's high desert, adobe homes relied on sun-dried earth walls over a meter thick. These walls soaked up the day's warmth and released it after dark. Even when nights fell below zero, indoor temperatures stayed between 8 and 12 degrees. A small stove sufficed for cooking, but the real comfort came from the earth itself. Across continents, thick walls and thermal mass shaped homes that worked with their climate, not against it. A thick stone or adobe wall is more than just a barrier, it is a thermal battery. Its performance can be measured with precision. Building scientists use the equation Q equals M times Cp times delta T to describe how much heat can be stored. Here, M stands for the wall's mass, Cp is the specific heat of the material, and delta T is the temperature change. For a cubic meter of stone or earth, a 10-degree swing in temperature allows that wall to soak up about 16 megajoules of energy. That's enough stored heat to keep a small room noticeably warmer through the coldest part of the night. But the real magic is in the timing. Heat does not move through a heavy wall instantly. It travels slowly, creating what is called a thermal lag. Scientists calculate this lag with the formula T lag is approximately L squared divided by pi squared times alpha. L is the wall's thickness, and alpha is the material's thermal diffusivity. For a 40-centimeter thick stone wall, the lag between the peak temperature outside and the warmth reaching the inside can be 4 to 8 hours. This means that by the time the sun sets or the fire dies down, the wall is just beginning to release its stored energy back into the room. Field tests back this up. In real homes, sensors show a clear delay between outdoor temperature drops and the moment the interior cools. Dr. Elena Martinez, a professor of building physics, has monitored historic earthen houses in Spain and North Africa. Her measurements confirm that thick walls can buffer indoor temperatures by several degrees, smoothing out both daytime heat and nighttime cold. The result is a home that maintains comfort with minimal fuel, relying on the predictable physics of mass and time instead of a thermostat. These numbers turn earlier builders' intuition into hard evidence and set a benchmark for comparing the true cost of comfort in traditional and modern homes. Throughout the 20th century, 5 powerful forces converged to push climate-responsive homes to the margins. First came the rise of industrial materials, mass-produced brick, steel, and later concrete. These allowed builders to put up houses quickly and cheaply, but the walls grew thinner and their ability to store heat all but disappeared. At the same time, new building codes began to favor standardized insulation values, measured as R values or U values, rewarding thin layers of synthetic material over the slow, steady warmth of heavy stone or earth. The rules were meant to save energy, but they ignored the comfort that comes from thermal mass. Urbanization added another layer. As cities densified, homes crowded onto narrow lots, often with little regard for the sun's path. The old logic of orienting a house for winter light gave way to maximizing floor area and squeezing in more units. Mechanical heating and cooling became the default, not the backup. By the late 1900s, the economics of heating, ventilation, and air conditioning had created a global market valued at around $150 billion. Manufacturers and builders promoted comfort as something you could buy, not something you could build in. Large windows and open-plan interiors, now possible with cheap glass and steel, became symbols of modern living, even as they made buildings harder to keep warm without constant energy input. Professor Hans Klein, a historian of vernacular architecture, sums it up. The shift wasn't just about better comfort or new technology. It was a social choice to trade a living, breathing envelope for mechanical convenience. What was lost in this exchange is more than just thick walls or clever layouts. It's the quiet resilience of homes that once worked with the seasons, not against them. Measured side by side, the energy gap is impossible to ignore. When researchers tracked 2 houses, one built with thick, heavy walls and compact design, The other with modern lightweight construction, the difference in heating demand was stark. The traditional home used 38% less energy to stay warm through winter. That number is not a rounding error or a quirk of climate. It is a hard metric, the kind that shows up on utility bills and in cold bedrooms. The study controlled for outside temperature, household routines, even the direction each window faced. Still, the high-mass home needed far less fuel. Every degree of warmth in these older buildings came from the walls themselves, not from a machine. That 38% gap is more than a statistic. It is a measure of comfort lost and of resources now spent just to reach what once came naturally. The rules changed. Builders chose speed and profit over lasting comfort. Codes rewarded thin walls and quick fixes, not the slow warmth of stone or earth. Industry pushed machines as the answer, making natural design seem obsolete. The old knowledge was set aside. Energy became a bill, not a resource to be stored. What once kept families warm for centuries was left behind, replaced by systems that need fuel every single day. Today, homes built with thick masonry walls, high thermal mass, and passive solar orientation are rare. Yet energy bills and emissions keep rising. As building codes evolve, the lessons of climate-responsive design grow more urgent. The future of comfort may depend on what we choose to remember and what we choose to rebuild.